Thank you very much for the kind introduction, and it's a pleasure to talk a bit about the research which we are doing in the theoretical chemistry. So what we are trying to solve is to solve the electronic Schrödinger equation for complex systems, and we try to do so as accurately as possible. Here you see the problem. The computational scaling scales very steeply with molecular size. So the closer you get to the exact solution of the Schrödinger equation, which in principle describes matter in an exact fashion, the steeper the scaling is. So it's an exponential increase of the computational effort. So what we are trying to do in my group is to reduce the scaling to linear only, while preserving the accuracy, while fully preserving the accuracy. The goal we have is then to describe systems like these. This is a DNA repair system. So it repairs defects in the DNA, or for example, these covalent organic frameworks, which are important for energy conversion processes. So the Schrödinger equation, of course, well known. We normally use the Born-Oppenheimer approach to simplify the equation. So we use the Clampton-nuclear approach. So the nuclear-nuclear interaction is a constant. And then the Hamilton operator reduces to the electronic Hamilton operator, which consists of the kinetic energy of the electron, the operator for it, the electron-nuclear interaction, and the electron-electron interaction. The key problem is the electron-electron interaction. If that term wouldn't be existing, then of course I wouldn't be giving this talk, because then the Schrödinger equation would be exactly solvable. But of course it exists. But let us assume first that we neglect the term. So one basically says we focus on the electronic Hamiltonian with just the kinetic energy of the electrons and the electron-nuclear coupling. So no electron-electron interaction term. Then the electrons are fully decoupled. So you can describe each electron with a spin orbital. So with just one orbital, it's a one electron function. And this is sufficient then to write an ansatz, like a product ansatz, which is written here. You have to respect antisymmetry, so the Pauli principle, in order to be physically correct. And this is given by the so-called Slater determinant. So it's an independent particle model which we use. So we use then this function to compute the energy with, and then we switch on the electron-electron interaction again with the exact Hamilton operator. So what we do is we use an independent particle model and then use the exact Hamilton operator. So this leads us to a mean field approach, the so-called Hartree-Fock theory. And it recovers about 99% of the exact energy. This is of course perfect. 1% error would be small. But if you think what kind of energy we are calculating, it's a huge energy. So it's the energy which becomes free if we build our molecule out of the nuclei, the positively charged nuclei, and the electrons. So the errors can be still huge. 1% is a huge energy. However, we need relative energies, because that's what we need in chemistry. And these are much more accurate than the errors in the absolute energies. Nevertheless, the remaining 1% to the exact energy is defined as the electron correlation. So it's the difference between the mean field approach and the exact energy. So what can we do in order to describe this electron correlation? So as I said, we have this Slater determinant, one particle functions describing our electrons. And then in order to solve the SCF and the Hartree-Fock equations, we expand our orbitals in Gaussian type basis functions typically. So here are the orbitals, the spin orbitals, and the basis functions, and we combine them by these molecular orbital coefficients. So what we get, of course, if we have a complete basis set, is an infinite basis set. We need to have a limited size of the basis set, but nevertheless, we have many more basis sets, basis functions than occupied orbitals. So upon diagonalizing the Hamiltonian, we not only obtain the occupied electrons, where the electrons are in, but also virtual orbitals. And these are great because it's very easy to write down that with these virtual orbitals, we can write down the exact wave function. This is the so-called full CI, full configuration interaction wave function. So it consists out of the single determinant, which we started from, so the Hartree-Fock determinant, for example, and then we excite or we build all possible determinants with n electrons. So what we do is we excite an electron from an occupied orbital to a virtual orbital. These are the singles. Then we can do this also for 2 electrons. It creates the doubles and the triples and so on. So if you have, for example, 3 electrons in your system, then you are done with the triples. You get the exact wave function and the exact solution. But of course, the row goes on and the computation effort grows exponentially. So what one normally does is one truncates the CI approximation. So for example, one stops after the doubles or after the triples. And then one looks how is the energy, for example, converging. There's one problem with truncated CI. It's not size consistent. I won't go into details about this, but typically one uses a very similar approach where these excitation operators, so creating the singles, doubles, triples, and CI, they are written in an exponential. So here are the T1 operators, T2, T3, creating, again, singles, doubles, triples. But since it's an exponential ansatz, the size consistency is guaranteed. And this leads to the so-called couple cluster ansatz, which is the most widely used correlation method if you want to have very high accuracy in a wave function based method. So just to illustrate you the accuracy here, the error in the total energy with respect to the exact solution for water and a hydrogen fluorine molecule, you see Hartree-Fock has an error of about 200 millihartree. Perturbation theory, second order perturbation theory, has about 10 millihartree. Couple cluster, singles, doubles, triples, quadruples converges very quickly to the exact result. So one can really describe the exact solution. The problem, of course, is that the computation effort increases very dramatically. And this is the hierarchy of methods we have in quantum chemistry. So we start, for example, with a Hartree-Fock wave function. This scales already cubically with system size. Then we can do perturbation theory. In the standard formulation, it scales m to the 5th. Then couple clusters, singles, doubles, m to the 6th, m to 8, and so on. A completely different approach is density function theory, which also in the way we solve it, it's a Cohen-Sham formalism, which we normally use, scales as cubic with molecular size, but there is no defined way to the exact solution. It's much more difficult to write this down. In principle, it could be exact, but the exchange correlation function is an unknown, and in this way lacks the direct connection to the Schrödinger equation. But there is, for example, the random phase approximation, which also improves upon DFT. It's an m to the 6th scaling method. And in my talk, I will show you linear scaling methods for Hartree-Fock, DFT, MP2, and RPA. What can we do in order to reduce the scaling without sacrificing accuracy? Well, Moore's law is well known. It has been formulated by Gordon Moore in the 60s. That the transistor density doubles every 18 or 24 months, depending on the formulation. And although it was a crude guess at the time, it held for many years. And even today, where the processors don't get even much faster anymore, it goes into parallel structures. So we have parallel processing, and it still holds in a way. So it's just amazing if you think back to the first computer of Konrad Zuse with 5 flops, and that with a simple graphic card, we are at 2 teraflops roughly for €1,000. So if we believe in Moore's law, then 15 years would correspond to roughly a factor of 1,000 in computer speed we gain. If we have 1,000 times faster computer and a linear scaling method, of course, we can calculate 1,000 times larger molecule. If it's cubic, the speed up of the computer is eaten up by the scaling, and it's just a 10 times larger system. And of course, the steeper scaling, the less large molecules we can calculate. So in a way, linear scaling quantum mechanical methods are really crucial to translate directly the computer speed into the computable size. just looking back, in 2004, the world's fastest supercomputer, the Blue Gene L, had about 70 teraflops, costing many millions of euros or dollars. And just 10 years later, we have a graphic card, for example, here of AMD with 1,000 euros, 2 teraflops. Well, we all know that the computer speed increased dramatically, but it's still amazing that for 35,000 euros, you can beat the largest supercomputer of 10 years before. The problem with these graphic cards is that they are highly complicated for quantum chemical codes. Quantum chemical codes consist typically of 1 million lines of computer code. So if you want to exploit the capabilities of these graphic cards where you have to distribute, for example, on one graphic card about 2,000, 2,500 tasks already, and if you have a couple of graphic cards, you are quickly at 100,000 tasks you need to distribute. So this is why one needs to rewrite the quantum chemical codes. And as I said, 1 million lines of code is quite nasty. But my permanent coworker Jörg Kussmann rewrote a quantum chemical code from scratch and created the code fermions, which allows to exploit these capabilities of these graphic cards. And I want to convey you a bit about the ideas. But let me first explain you what we can do for reducing the scaling of Hartree-Fock and density function theory, which are very similar in their Kohn-Sham formalism, in reducing the cubic scaling down to linear. Well, this is the eigenvalue or pseudo-eigenvalue equation of Hartree-Fock or density function theory. Here in Hartree-Fock, you have the Fock matrix. In Kohn-Sham theory, you have the Kohn-Sham matrix, and you diagonalize this Hamiltonian. And then you get the molecular orbital coefficient matrix. This describes how the molecular orbitals are formed by the basis functions, so our Gaussian type basis functions. But if you look at this quantity, here the quantity is plotted, this is coefficient matrix, and we plotted all the zeros in this matrix in black and all the non-zeros in color. It's for a simple DNA system. Then you see basically all elements are significant. So the canonical molecular orbitals, which one gets out of this equation, they are delocalized over the entire system. However, if we build out of this coefficient matrices the one particle density matrix, or summing over the occupied space, then we get a quantity which is much more physical, because the molecular orbitals, in a way, they are non-observables. But if we have the one particle density matrix, it couples the Gaussian type basis functions to the electron density, which is of course an observable. So the behavior of the one particle density matrix is much more physical than the one of the canonical molecular orbitals. And here you see the behavior for typical system, a DNA system. The blacks are the zeros, and you see the colored elements, they scale only linearly with molecular size. So there's a lot of sparsity, and that's what we need to exploit in order to be able to treat large molecular systems. So if we want to calculate, for example, the Fock matrix in a linear scaling fashion, we need to contract this one particle density matrix with these two electron integrals. We have a Coulomb type part, where the scaling can be reduced by the so-called fast multipole method, continuous fast multipole method by Chris White and Martin Head-Gordon. And then we have the exchange part. This exchange part is built by the summation, so it's the Einstein sum convention I'm using here, over lambda sigma. So we couple the two sides of the two electron integral, and this reduces the scaling down to linear if the one particle density matrix is a local quantity. So if we have a block of gold atoms, we have a non-local system. But for many other systems, we can exploit this locality. And this is the important feature of linear scaling methods for Hartree-Fock and density function theory. And then we can get wins like that. Here, computation time plotted against the system size. Here you see the standard method, and here the linear scaling method. The wins are large, and of course they get bigger the larger the system is. The accuracy is exactly the same. So we have a numerically fully controlled scheme, so we don't lose accuracy. So, but if we go back to the question, how can we exploit graphic cards or parallel structures, which are most common in quantum in computer technology today? The important point is that we need to formulate methods which allow us to distribute the tasks before computing them. So we cannot do, for example, here an element-wise estimate of the quantities which we need to contract here informing the exchange. We need to have a pattern which we need to determine beforehand, and then we can distribute the tasks on GPUs. And this is done by this so-called pre-Decay method introduced by my co-worker Jörg Kussmann. So Jörg Kussmann was the one rewriting the quantum chemical code from scratch. He's a permanent co-worker in my group that has done great work on this. And here you see the efficiency of this code. So for example, if you have 40 graphic cards, you are distributing already about 100,000 tasks over the graphic cards. The time for one Fock build for Hartree-Fock theory in 2017 with 11,000 basis function was about 1 minute per Fock matrix. So parallelization helps quite a lot, but also methodological improvements help quite a lot. So this is most recent work by Jörg Kussmann and my PhD student Henrik Lacroix, where you see here the performance in 2000 or this year on the 1,000 atoms DNA system. On just one graphic card with even more basis functions, it takes about 24 seconds per Kohn-Sham matrix. So the speed is quite amazing what one gets today. So one can really describe also the dynamics of these systems. The typical speedups we get as compared to other modern program packages are a factor of 100 to 1,000. We also employ semi-numerical integration of the exchange. So one part is integrated analytically and the other one numerically. And this also allows us to use GPUs very efficiently. And this is work by my PhD student Henrik Lacroix together with Jörg. And here you see an example, again, this 1,000 atom DNA system. Conventionally, this is already our fast linear scaling method. It takes about 100 times less with the new method, the semi-numerical Decay method for GPUs. So the speedups are quite amazing. And in this way, one can really describe also the dynamics for complex systems. So far, I've been talking about Hartree-Fock and density function theory. What can we do if we want to move to electron correlation beyond DFT? So, for example, perturbation theory to second order, m to the 5th method, or random phase approximation, m to the 6th method. What's the idea about it? So let me describe briefly the goals in describing electron correlation. So we want a low or linear scaling, and sometimes even sublinear scaling method for some properties that works if it's a local property. We want to have full control of the numerical accuracy, and we want to have the full accuracy independent of the delocalization of the electronic structure. So in a way, we want a linear scaling method for a local system. And if we hit a system like a block of gold atoms, then we still want to have the exact result within the correlation method we are using. But then, of course, we revert to the old scaling. But still, it's an ab initio method in this way because the result is always the correct one. And then we want to have accuracies of sub-milli-Hartree or micro-Hartree accuracy in the absolute energy. Just to give you an example, a DNA system with 4 stacked DNA base pairs, 260 atoms, the correlation energy is 36 Hartree. If we have an accuracy of 99.9%, then we would get an error of 100 kilojoule per mole. So it's a huge error. So we need really high accuracy if we don't want to rely on fortuitous error cancellations. So high accuracy is clearly what we want. The basic idea behind getting to a linear scaling correlation methods, what we have been following for many years now, is if you think about the 2-electron integral, so a 4-center 2-electron integral, 4 basis functions and the 2-electron integral, then 2 basis functions describe the charge distribution for electron 1. The other two base functions, the charge distribution for electron 2, and they interact in a 1 over r fashion. And of course, you need to integrate over all charge distributions in space. So this is the integral. In quantum chemistry, one normally estimates the size of these two-electron integral using the Schwarz estimates. This upper bound, or rigorous upper bound, was introduced by Marco Heyser and Reinhard Arichs in 1989 and led to the success of SCF methods at that time. So instead of a 4-center two-electron integral, we just have 2-center two-electron integrals. So it's much, much easier to compute. But if you look at the estimate, you see there is no 1 over r coupling in the estimate anymore. So the 1 over r decay behavior is fully missing. This is not important if you think about a Coulomb type interaction. 1 over r is a slow decay. But in electron correlation methods, this 1 over r decay reverts to a decay of at least 1 over r to the 4, and if not 1 over r to the 6, which is the typical decay behavior. Let me illustrate this. If we plot here the size of the integral with respect to the distance of these two charge distributions, then the exact behavior is here the 1 over r behavior. The Schwarz estimate here in the upper part is not feeling any or has no information on the distance of the two charge distributions. But and then in order to get this distance information again into our integral estimates, we first formulated the so-called multipole-based integral estimates, which allow to reintroduce this 1 over r coupling. And then basically we formulated a much better way, which is the coupling between the Schwarz estimates, here denoted as Q, divided by a distance which extends from multiple considerations. So this allows us to really estimate the two-electron integrals and then to discard them, and with the 1 over r decay behavior included. So how we do such a formulation in, for example, Möller-Placid perturbation theory, so MP2 theory. This is the expression one needs to calculate. And the problem is the transformation of the integrals from the AO into the MO base. Here you see MO integrals divided by the orbital energies. So one cannot simply write this expression in an atomic orbital base. This is not possible. However, in the 90s, Jan Almlöf and Marco Heyser came up with the idea of using the Laplace transformation. So writing this 1 over the energy denominator as an exponential. And once you have the energy denominator in the exponential, then you can decouple the orbital energies. And this allows you to write everything in the atomic orbital base. So in a way, we move away from these transformations divided by the orbital energies towards this Laplace transform. And then we collect these molecular orbital coefficients in an expression with the exponential. So here, the e to the epsilon I and the Laplace integration. So this is a pseudo-density in the occupied space, and this is a pseudo-density in the virtual space. So everything is now in the atomic orbital space, and the expressions look like that. You have these transformed integrals, transformed with the occupied and virtual pseudo-densities, and then you contract them with the normal integrals. However, the question is now, how can we really then estimate the contributions rigorously? And there our integral estimates come into play. But let me first show you how we can describe such a two-electron integral in a multipole expansion. So if we have well-separated charge distribution, we can expand the two-electron integral in the multipole expansion. So we have the monopoles and 0, then the dipoles, quadrupolar terms, and so on, and higher order terms. Upon the transformation of these monopole terms, so the overlap terms, the transformation with the occupied and the virtual space leads to 0. They are orthogonal, so they drop out. So all the terms m to the 0 drop out, and the first remaining term after transformation is this dipole-dipole term, which decays as 1 over r to the 3. So with that, we can show that this is a 1 over r to the 3 term combined with the 1 over r term of the 2-electron integral. So we have at least a 1 over r to the 4th decay. For the exchange, it's even more because it's an exponential coupling of the charge distributions. With our QQR integral estimates, we can then reduce the scaling to linear, and here you see the result, computational time plotted against the system size. We see here the standard methods, the traditional methods scaling Sm to the 5th, and you see here the linear scaling method leading to new possibilities. Already the early points are cannot be calculated with the traditional method, so they need to be extrapolated. And then the efficiency, just illustrated for this DNA system I showed you earlier, 1,000 atoms, instead of m to the 5th, we have m. So the time for such the Coulomb type contraction with an MP2 in 2013 was roughly 1 or 2 months as compared to the conventional calculation, of course, extrapolated 100 years. Today in 2020, we are at a time of 1 or 2 days on a single node with most recent developments by my 2 PhD students, Michael Glasbrenner and Daniel Graf. What about the random phase approximation? Can we use the tricks which we are using for MP2 theory? Well, again, this is Laplace transform for MP2. If we do the same for RPA without going into details of the equations, then we see that there is a coupling between the orbital energy of the virtual space and the occupied space. So there is no decoupling by the Laplace transformation. And this, of course, kept my former PhD student Henry Schokus quite busy, but he came up with a great idea. He used such a double Laplace transformation, we call it double Laplace transformation. It's a sine function combined with an exponential. And then you can rewrite the whole equation again in these pseudo-densities, occupied and the virtual ones. So then we have again an AO reformulation which we can introduce. What we use in addition, I didn't talk about this so far, is that we decompose these pseudo-densities. So this is a pseudo-density. In red, you see the significant number, the significant elements. In white, the zeros in this matrix. And then we use a Cholesky decomposition. And this Cholesky decomposition allows us to reintroduce the occupied space, which is an important feature if we want to go to large basis sets, because the basis set space is much larger than the occupied space. Same we can do for the virtual space, but there the winds are much smaller. This is the time for the RPA method we have today, DNA fragments. These methods were developed by Daniel Graf, Matthias Beule, and Henry Schokus, my PhD students. And you see here the computation time plotted against the system size, here the conventional methods. Just to show you the accuracy, if we start from a typical density function like PBE, we see the errors here plotted. This is without empirical dispersion correction. Dispersion is a big problem in standard DFT methods. And here the direct RPA reduces the errors quite considerably. And if we introduce here, for example, the screened order exchange part to the RPA method, then we really reach chemical accuracy. So with these developments, we have a whole zoo of methods which can be very efficiently applied to large systems. And just to show you an example, here the DNA repair, which is an important subject, of course. Here you see a damaged base, which is turned out in the enzyme. And with our methods, we're able to describe large quantum spheres of the system in order to describe the reaction mechanism and to understand how these enzymes repair DNA, how do they cut the damaged base in order not to damage the whole genetics. Here you see the 3 different systems all showed the same behavior. I don't want to go into details there, but it was interesting that we found a mechanism which basically is base independent, having important implication for the base cleavage. Well, with that, I hope I was able to show you that the development of these linear scaling methods is quite helpful in treating very large and complex systems. Of course, we want to go higher and higher up the hierarchy. There are already very nice methods in the literature for reducing, also for cluster theory, the computation effort. However, the prefactors are, of course, not small, and of course, the accuracy is always an issue. So there is still a lot of work to do, which will keep us busy. The work was done by my group. I mentioned already Jörg Kussmann was a permanent co-worker and was developing the fermions code, but also the work by all the others was very helpful. Thank you for listening.
Thank you, Christian. It was extremely interesting to learn about these methods and also to see how also hardware develops rapidly. So the computations become so fast. And I suggest then we simply shift now to the round tables, and I invite all the listeners and attendees who want to ask questions and discuss it, join there. You find it in the Meet Anyway space, conference space.